Cool, well thanks for inviting me to speak at this workshop. It's really exciting to be here. It's a great list of speakers. I'm honoured to be able to sort of open the workshop. So, okay, sorry, technical details.
Let's see if this is good.
Okay, yeah.
Better?
Yeah, is that alright? Clearly should have worn an outfit with a waistband. So, just to begin with, it's kind of acknowledge my co-author on a lot of this work, which is Trevor Hoy at the University of Glasgow, and also just the Royal Geographical Society, who gave me some money, which covered some of the experimental costs. So we're going to start by, so over the next sort of 3 days, a lot of the time what we're going to be thinking about is alluvial rivers. And if you think about alluvial rivers, we're thinking about these sorts of sets of relationships, so between sort of channel morphology, flow, sediment transport, the way in which they interact with each other. And I guess we're going to argue there's still quite a lot that we don't know about these different relationships and how they operate in these types of systems. But what we're going to start with for the first hour or so of this workshop is actually looking at something a bit different, and that's thinking about how these sorts of relationships operate in bedrock alluvial systems. And I guess I'd argue that actually we probably know even less about how these relationships operate in these bedrock alluvial systems. So one of the main differences between these sort of two different types of rivers is that instead of a single channel morphology in the alluvial system, we have these sort of two components of the bedrock alluvial systems. One is obviously the bedrock, and the other one is some sort of alluvial cover on top of that bedrock surface. And part of the reason that bedrock alluvial systems are in many ways a bit more complicated is that those two components can evolve at quite different timescales. So clearly the sediment cover can change over the course of a single event. We have quite large amounts of sediment transport, sediment supply that can alter that cover. But whereas the bedrock morphology tends to evolve over far slower time periods. And there have been examples, obviously, of where bedrock morphology has changed a lot during a single event. But on the whole, it tends to evolve either during individual very large events or as a sort of integrative response to all the previous flow events that have occurred within that channel. So as a result of this, you could argue that actually the bedrock morphology in the system can always seem to be sort of out of equilibrium with the sort of standard day-to-day flow conditions because of this fact that it's either a response to either really large events, or if it's an integrative of all the previous events, it could actually evolve during conditions that actually no longer occur within that river channel. So what this means is that we've got sort of two sets of processes here, and I guess the question is, if we've got this bedrock morphology, which is potentially out of equilibrium, what impact does that have on all these different relationships sort of within this system? The other way in which this set on the right slightly complicated is the fact that the way in which the bedrock morphology has changed is clearly through these erosional processes, and the sort of grey arrows represent a second set of feedbacks which relate to the evolution of that bedrock morphology. But what I'm going to be talking about today is a situation whereby we kind of assume that the bedrock morphology is static, so we're talking about sort of fairly short-term events. So what that means is that if we want to understand sediment dynamics, hence the title of these talks in this bedrock alluvial systems, we can't really just sort of understand these in isolation. We actually need to think about how they sit into this context of all these other relationships which are going on within these channels. So I thought it would be useful just to sort of start with a bit of a recap of the different types of relationships that we know about in bedrock alluvial systems and to try and sort of outline some of our current levels of understanding. So the fact that we've got these two different phases means that that has quite a large impact on sediment transport. So as a result, sediment grains in a bedrock alluvial system, they can either be on the bedrock part of the bed or they can be in a sediment patch. And if you do a sort of simple force balance analysis and sort of set the grains up like this, so these are alluvial grains, these are bedrock grains, and use a sort of Kirchner pivoting model, you find that generally the grains on bedrock have a critical shear stress which is about an order of magnitude less than those on the alluvial areas. So those grains are very easy to entrain. Consequently, you also find that sediment grains tend to get deposited in alluvial places, and so you get this sort of move from a distribution of grains to those very sediment patches forming, such as sort of the work of Nelson and et al. Has demonstrated. Also, the work of Giddy et al. Has demonstrated that actually the shape of the bedrock itself can have a different impact on sediment entrainment. So if you've got ribs, that can actually alter the size selectivity of sediment movement. depending on the rib orientation, and also kind of where grains are in relation to the ribs themselves can also unsurprisingly impact how easy it is for those grains to move. If we've got these large areas of bedrock that are very low to the critical shear stresses, we'd expect that that's going to, once grains get in motion over those parts of the bedrock, they're just going to travel very easily, and they can travel quite long distances without a lot of sort of deposition occurring. And I don't know of any sort of great data sets for demonstrating this, but you might suppose that actually that means that bedload transport rates, once sediment is in motion, may be a lot higher over bedrock parts of the river than they are in comparable alluvial channels. And this is about the only comparison data set that I know of. This is some tracer data from the Calder, which is bedrock alluvial, and the Alpty Beg, which is fully alluvial. And they're basically similar grain size distributions, similar sizes, similar slopes. And you can see that the virtual velocities in the Calder are about twice, if not a bit more, than those in the Alpty Beg. If we think about sort of how the morphology influences the sediment cover in these systems, then we can see that actually morphology can also be quite important, the shape of the bedrock. And sediment cover is one of these things that's been looked at quite a lot in the literature, largely in the context of kind of trying to understand bedrock incision, sort of in the context of landscape evolution models. So there's quite a lot of interest in sort of bulk sediment cover. So if we've got a reach river, how much of the bedrock is covered up at a given time? So sort of Chantavard and Parker have done some work here. Well, they've demonstrated that if you've got a reach with boulders in the bed, you get this relationship here. So this is sediment feed, basically on this axis here. This is bedrock exposure on this axis here. And if you put the boulders in, you actually get quite a linear relationship between the two. In runs without any boulders, you actually have far less sediment cover for the same sediment feed. So it's showing that the boulders are creating areas, sort of areas of wake behind them when sediment can start to be deposited, and affecting the way in which that sediment cover develops. But the thing is that this sort of work was, although it was obviously run within a reach, the sort of results they were looking at were reach scale properties. But clearly, we only want to say, well, what's happening within a reach? And we know that it's kind of obvious that if you've got an area of bed like here, it's got lower elevation areas, we'd expect sediment's going to accumulate in those lower elevation areas. But we don't really know whether it's just elevation that determines where sediment accumulates, or whether there's maybe other factors as well that are also at play. If we then got this sediment cover developing on this bedrock surface, it's obviously going to have an impact on the roughness of the river. And there's another sort of set of research questions here about how do we actually quantify the roughness of these bedrock alluvial channels. So some of the work that sort of Joel has been doing and Inua et al. Have sort of been saying, okay, well maybe we can just treat roughness as some sort of linear combination. So we get a representative roughness strength for the bedrock areas, a representative roughness strength for the alluvial areas, and then it's just a sort of proportional relationship depending on the relative proportions of those two areas. But obviously there's a question here about what is a representative roughness length for both the alluvial and the bedrock parts of a bed. And then some other works developed that actually this representative roughness, this difference in roughness is actually quite important, particularly the relative roughness of the bedrock and the alluvial areas, because both the sort of flume work of Chantavard and Parker and also some of the modelling work that's been done has demonstrated that actually this relationship that you get between sediment flux on these axes here, and this is bedrock exposure, this is cover here, is actually quite dependent on the relative roughness of those two areas. And in this case here, we get quite different relationships. So this one sort of demonstrates hysteresis, whereas this one doesn't. And in this case here, we've got relatively smooth bedrock, and in this case, we've got relatively rough bedrock. So in order to be able to quantify the roughness, it's actually quite an important thing to be able to do. So what this means is that sort of, in order to fully understand sort of sediment dynamics within these bedrock systems, what we really need to be able to do is to actually understand how they sit within the context of sort of all these other relationships within these bedrock alluvial systems. And potentially, when we're looking at these relationships, we kind of maybe need to consider this idea that the bedrock morphology that we're working with may not necessarily be one that's been produced by those relationships that are currently operating in the system. It may be one that's almost effectively imposed because it's been created under slightly different conditions. The other thing we need to think about is at what scale are we trying to understand these relationships? Like I say, a lot of the previous research has often been motivated by this desire to be able to predict bedrock incision for landscape evolution models, in which case the sort of timescales that we're looking at are sort of centuries, even sort of millennia, and in which case, you know, reach average conditions are probably as small a scale as you want to get, and ultimately you may want to be thinking of the larger conditions. But the same question is that, I guess what, just jumping ahead of myself, so okay, if we take the reach, we know that there's a lot of variability within a bedrock reach. And the question is what impact does this sort of smaller within reach scale variability actually have on these reach average properties? So if we want to be able to predict reach average sediment cover, even for a landscape evolution model, do we actually need to think something about kind of this levels of variability that's occurring within the reach? Or can we just ignore it? Does it just kind of average out and actually it's not really relevant? And so I guess we need to assess the spatial variability of the processes occurring within this reach. And just for an example, if we take this particular reach here, you can see we've got this lower area over here. We might argue it's got low elevation. That's going to encourage sediment to be deposited in those parts of the bed. That's going to increase the roughness, which is going to decrease the flow velocity, and maybe produce more sedimentation in that area. Whereas if we look at this part of the bed here, we can see we've got a bedrock area, higher elevation, it's going to less roughness, higher flow velocities, and hence less sedimentation occurring. So you can already see in sort of two adjacent areas, we've got very different feedback loops going on, which is sort of helping to perpetuate that difference between the two. And obviously there's a question here, okay, well what does this mean for the pattern of erosion that's going to occur within this channel? You know, which parts of this area are going to incise, which parts are going to stay where they are? And what does that also mean for the long-term sort of morphological evolution of this channel? And those two questions are kind of ones that I'm going to leave to one side for this talk. Okay, so what I want to present today to kind of sort of address some of these questions is basically a 1 to 10 scale model of a section of Bedrock River that we've been working on. So this is the model here. I'll come to how this model's been developed, but basically it's a 1 to 10 Froud scale model. So the sort of research questions that we're going to be addressing in this series, this talk. So we've got 4 questions. So the first is, how does the spatial pattern of hydraulic properties vary with discharge? So kind of what's the spatial pattern of flow that's kind of induced by this bedrock morphology? And kind of how is that flow affected by the roughness of both the bedrock morphology but also the sediment cover on top of that morphology? And also, how does the sediment cover itself develop as a function of both the morphology and the flow conditions? And to what extent is that morphology, does that determine the location of those sediment patches, but also the stability of those sediment patches? So this is the river that we've been working on. So this is Troutbeck in the North Pennines. And it's limestone bedrock. And that means we get this sort of quite blocky topography here. You can see we've got sort of bedding planes, and then we've got sort of vertical joints between the bedding planes, which get eroded. There's quite a lot of abrasion going on, but there's also a certain amount of chemical weathering, which is producing that topography. And this is the reach that we've been working on. This is what it looks like under really low flow conditions. And this is what it looks like under sort of getting off of bank fall conditions. The reach's got about 22% sediment cover, so it's a lot of exposed bedrock. D50 is about 70 millimetres, D84 is about 15 centimetres, slope is 0.02, and the reach is about 9 metres wide, and the bank fall discharge is approximately sort of 10 cumex. Okay, so this is how we actually created that model. So what we did was we took this section of the reach here, so this is a section about 18 metres long, 9 metres wide, and then basically scanned it using a laser scanner. So we get scanned it from sort of 4 different directions, and we get a very high sort of point density of about 33,000 points per metre squared. Unfortunately, laser scanners don't work that well through water, so there's still 20% of the reach that had to be surveyed in a different way, and that was done using differential GPS. So that's got a fairly lower point density of about 43 points per metre squared. So what we did is we took those 2 data sets, combined the two, did quite a lot of point cloud processing, quite a lot of tidying up and registration, and eventually managed to produce an interpolated surface topography of this section of the reach. Once you've got that topography, there's a whole load of other sort of processing steps in order to actually create it into a structure, an object that can actually be 3D printed. And so this topography here was converted into 6 different tiles, and those 6 different tiles were 3D printed and then installed in the base of the flume. So basically this section here is a 1:10 scale model of this section of the bedrock reach right up there. So once we've got those tiles that have been printed and installed in the base of the flume, we installed a section of coarse gravel upstream, a section of coarse gravel downstream, and the Reynolds numbers from the experiments demonstrate that we had sort of fully turbulent flow over the measurement section down here. Now there's sort of 2 sets of experiments that I want to talk to you about. The first one's a series of experiments looking at flow. So what we did was we ran the flume under 5 different steady discharges between 20 and 60 litres per second. And each one of those discharges, we took ADV readings from one of 18 locations across the bed. And that's what you can see with these purple dots up here. Now each of those locations, we've got 3 minutes worth of ADV data, and we've also got the water depth that occurred in that location. So the second set of experiments actually introduced sediment into the flume in order to try and look and see where these sediment patches developed. So we started off with a scale grain size distribution. So this has got a D50 of 7 millimetres. And in the pictures you might see there's some coloured grains. The D84 is painted yellow, the D50 is blue, the D16 is orange. And what we did was in this run, we sort of let the flume equilibrate and would study flow, and then we introduced a mass of sediment at this upstream end of the 3D printed tiles. So instead of introduced it here, we let the flume run for 5 minutes, so that sort of sediment sort of patches became stable under that flow condition. And then we slowly ramped the flow up from the starting discharge up to about 70 litres per second, which is about the sort of maximum capacity of the flume. And as we ramped that up, it took, if we started at 20, it took about an hour to get up to 70 litres per second. During that time period, we took a photo of the bed every 5 seconds. So we've got a very sort of high resolution data set of where that sediment was. And then we used a sort of image analysis routine in order to segment out the sediment patches out of that bed. So we've got a very high resolution data set of how that sediment cover has changed during that hour. During the experiment runs, we also collected ADV data from just a single location in the flume, which is up there. And then the sort of combinations that we used of both sediments and starting discharge and sediment mass. We had 3 initial discharges of 20, 35 and 50 litres per second, and then sediment masses of between 2 and 16 kilograms. Okay, so this is an example of what one of these flume experiments looks like. So you can see we've got the sediment mass comes in at the top, quickly forms sediment cover, and then now we've got that flow ramping up. You can see that we get the sediment patches, they sort of stabilise and then they start to erode. And you can see that there's this particular area of the bed up here, which is kind of the sort of elbow shape, which tends to be quite stable for sediment, so we often get sediment patches forming in that location. And you can also see that the way in which the sediment patches break up tends to be, I'll just run that again quickly. The way in which they bend up tends to be sort of quite episodic, and they tend to be stable, and then it's like one grain goes and the whole sort of part of that patch then moves shortly afterwards. You can also see that not all patches sort of get entrained and move downstream. They kind of often move from one area of the bed to another sort of area of the bed slightly further downstream, and you get this sort of travel along this area down here. Okay, so just to start with, I've said this model is scaled. I guess I should probably show you some data to try and convince you that it actually does seem to be scaled. So unfortunately what we don't have is any data from both the field and the flume from a sort of comparable set of discharges. And so the field data we've got is from fairly low discharge events when it's actually safe to get in the river, whereas the flume data is from relatively high discharge events where the flow was actually deep enough to be able to sort of measure properties of the ADV. But if you sort of plot